go quickly. Okay. I'll try to finish in about 30, 40 minutes or so. Hopefully, maybe faster. So in this presentation, I will mainly do some environmental scan because I've already done a lot of environmental scan yesterday and earlier in the first presentation. So this part I might just move faster. And then and then I will talk about some fundamentals for practicing and doing research in data-intensive environment. And then I'll share information about a few of my recent research projects. So the overview of eScience and the big data, I'll go through quickly. And eScience, I think I already covered it. It's large-scale science and collaboration enabled by the internet. So network, large-scale, high-performance computing, and these are the main characteristics of eScience. And I think I used this diagram in the first presentation. I won't, go over it again. I'll just skip it. And here is another. Excuse me. Excuse me. So in all these data-intensive X, right? Like I said yesterday, there's also, if you talk about, there's other things about X informatics. I believe many of you have heard about social informatics and bioinformatics, right? Biomedical informatics, geoinformatics, ecological informatics. So there are many such informatics. And the X informatics, there are a few features. And these features are, they have experiments and instruments and other archives, literature, simulation. They all go into some kind of repository database. And then users get ask questions to these informatics resources and then get answers. So no matter which informatics you are in, geoinformatics, bioinformatics, biomedical informatics, and there are some generic problems across fields. One is data ingest, and it's mainly from the technical aspect. Data ingest, managing petabyte data, common schema, schema for databases, schema for metadata, schema for storage and all these, and then how to organize it and how to reorganize it and how to share with others, and query and visualization tools, all these, and building and executing models, integrating data and literature, documenting experiments, curation, and long-term preservation. These are common generic problems across all fields. And you can probably see that all these common problems have a lot to do with our information science. Because we, in information science, we do organizing information all the time. We do management all the time, and we deal with technologies all the time. We have information retrieval. All those are all these are very relevant to information science. But before we can do research in this X informatics or data-driven X kind of a research field, and we need to understand what are data. And you may laugh, what are data? This is very straightforward. You don't need to ask, but it's not that simple. Okay, so let's see. And this diagram, I think I used it yesterday. You can see the data collection mechanism, instruments from the air, remote sensing, and all these microwave towers and remote sensors in water, in land, on trees, and also these towers to transmit and readers to transmit data. And what are data? And that's different, very different data, type of data. You know, DNA sequences, chemical structures, you know, and organized in different structures, and healthcare data. And I think we are all familiar with this shelf after shelf of paper record for our medical records, right? And these days, if you go to, at least in my clinical, if I go to see a doctor, now the doctor no longer hold a piece of paper and a pen. They use iPad, just directly access the patient records, and then, you know, key in the information as they talk to the patient. And the image sensing, and also the many medical instruments collect the data from patients. And medical and health data you have, and this is the charter, a charter for health data, and there are many dimensions: privacy, technology, and secondary use, stewardship, uh, accessibility, availability, data quality, and all these issues, and standardization, compliance to regulations and policies, and security. All these are associated with data. So if we want to do research with data, and we also need to know the multi dimensions of data, like research orientation. Like yesterday I mentioned, research context, different types of research generates different types of data, um, and data types, and levels of processing. And these concepts are all described yesterday. They are data formats. So I'm going to show you some examples. Like scientific data formats, there are physical data format, bytes, bit bytes, these characters, strings, and there are data structures and meta formats. We all know CSV, XML. These are, you know, meta formats and can be read and processed by most of the software. And there are scientific specialized data formats. And I'm only giving you a few categories of examples. And then there are also data models. So these are the scientific data formats. And give you a specific, you know, let's drill down to scientific and medical data formats. If you look at medical and physiological data formats, there are, you know, bio-semi data format, EDF, and there are molecular biology data formats, PDF, that's for protein, and then there's a format for GenBank. You know, there's many. I'm just listing here very few examples. And metadata imaging, that's DCOM, that's another popular data format. And chemical formats and bioinformatics formats, and this is not by no means complete list of data formats. So to summarize it, scientific data formats are closely tied to scientific computing. So for each data format, and there will be a tool, you know, software associated with it, because, you know, the special characters and the features require that special type of software to process and analyze it. And that's the special, you know, special attributes of scientific data formats versus the tools used to, you know, perform science in this. So within all these, we need to have some basic concepts, some basic ideas about data structures, data models, and attributes, as well as we, you know, because sometimes data formats are associated with whether, you know, you can tell whether a data set is self-descriptive, like one of the I think the CDF data type, that's I can't, but it's one of the the earth science kind of data formats. And it has the header section for the numerical data before the data tables. So if you know this special data format, you will know this kind of data sets tend to be self-descriptive, because at the header section, it has the metadata, tells who created this data set, when the data set was created, and some basic in how many data fields there are, and what are the field names. So these are the basic information about the data set. It's embedded in the data set itself, and this is called self-descriptive data sets. But there are many other data sets that are not self-descriptive, which means they do not have metadata embedded in the data set itself. So there's a whole, uh, field of this data format theories and, I think tradition conventions to understand, to learn, and how these different data formats can interoperate between, whether this format can be read by other software. That's for a different, kind of data format. And we also need to understand no one format fits all standard. That means, like yesterday I mentioned, for some scientific metadata standards, there are usually hundreds of data elements. And when you are using these kind of data metadata standards to create this representation or description about data sets, then it takes very long time to finish. And especially if you are a third party, you are not the original data creator, but you are a librarian trying to help, and you have no knowledge about the history of the data set, and you don't even know where to find the documentation about the data set, and then that can take even longer to finish creating a metadata record for the data sets. So that's something about the metadata, and understand the metadata formats, data formats, and what are the impacts on the data management processes. And each standard has one or more tools for creating, editing, and annotating data set. So giving you an example, the DNA sequence that are covered by GenBank, which is an international data repository, are supported by at least two different tools for data submission, for data entry. So these two data tools are very different. Okay, so that means for one data repository, you have multiple. I think now they have a new tool which is web-based. Usually, in the old time, like back in the 2000s, they are still use the standalone software to enter the data and then FTP it to GenBank repository. But now they have a web-based tool for scientists, for biologists to submit data directly through the web interface. So that's a case of more than one tool to support the GenBank data format, metadata format. So there are, so when you are dealing with data sets, you also want to understand the data sets have different sizes. Some are very large, some are small, and there are also collection source types. Some are from the field observation, some are from sensors, and some from simulations. So understanding the research types will have value for you to understand the collection source type and you will have better understanding how to deal with this data, if how to check the data quality. Okay. And discipline, for ecological research, the data are sometimes from the like say from instrument placed in the wilderness, say in the lake. If you want to collect water quality data, you have some instrument and placed in the water under some buoy, and then that sensor, that instrument can I think can remit the data directly to the computer server. So our university has a professor who does this kind of research. And in astronomy, the data set will be mainly from either from telescope or from some kind of like the gravitational wave research. Data will be collected from a kind of a device that's like, I don't even know have that name, that interferometer. I think it's a very 1 kilometers long, and then here they have a laser device, and then another side is 1 kilometer long. So there's a device there. They shoot something into the laser device, and laser device shoot I think reflect, and they collect the data through that way. So anyway, astronomy have very different ways to collect the data from other disciplines. So you need the reason that I mentioned discipline differences is that understanding the nature of each discipline's research, you will have better idea what kind of data you are dealing with. Okay, and the size, the format, the content, and they are also level of interpretation, measurements, excuse me, measurements, observations, and derived observations, synthetic observations, interpretations, and I think these are usually taught in PhD level research methodology courses. So that's and data structure I mentioned earlier. So I'm giving you a couple of examples. This is one type, the kind of a data set we are familiar with, numerical data. And then this example I showed yesterday, this is interactive data set. So you have an interface for users to interact with the data set and the clinical data set. And what's common among these examples is that the attributes of a data set tell users or data managers about what the data set is about, how data was collected, to which project the data is related, who are responsible for data collection, who you may contact to obtain the data, and what publications the data have generated. So it can address many other questions depending on which discipline the data belongs to. This is an example about metadata in medical and healthcare sciences. So for structure, the metadata structure, you'll have the standard HL7, that's for healthcare. And for medical images, you have DCOM, that's what I mentioned earlier. It's also a data format standard. And bioinformatics, you have GenBank, and there are a number of bioinformatics informatics. There are a genome metadata standard, and then there's this is DNA RNA sequence. And for semantics part, so for metadata, usually we divide, between structure and the semantics, which is the value within the metadata value. So NCBI taxonomy, NCBO bioportal, United Uniform Medical Language System, MASH, subject, and all these. I think our professor Mauricio is an expert in this field. The data sets, data collection, and data repositories, these are related concepts, but they each of them has a different implication. So usually data collections are built for larger segments of data of science engineering. Data sets are smaller individual physical files that contains data, typically centered around an event or study. Like a few years ago when I teach the scientific data management course, I like to use an example that is called Buffalo Blizzard in 2000. So in that weather event, the devices recorded the snow, precipitation data and the wind speed, temperature, and all these in different locations around Buffalo. That blizzard was very famous. So in that case, all the data sets generated, the Doppler reader, the instruments recorded this numerical value by, say, in a time interval every 10 seconds or every hour. These data have a large number of data files in different format, in different categories. And for all these data, we call it a data set, because this data set record the data about that particular event called Buffalo Blizzard, in 2000. And of course, a data set can be small and can be large. This is a very large data set example. And there are smaller data set examples too. And data collections and the data sets are usually stored in data repositories. So in the data repository, you could have individual collections, and under each collection, you could have multiple data sets. And on the data sets, you will have individual data files. So these are the relationships between these terminology. I think as a data scientist, and these are basic knowledge you should, we need to have. So there are exciting opportunities and practical challenges and implications for scholarly communication process. So if we think about research as a scholarly communication process, and there are three big areas. One is publishing. Now, in the past, we all talk about publication of papers, books, right? But now data publishing is on the rise. And data publishing can also get you credit. And this credit can be counted towards your academic evaluation. For example, performance, for example, tenure and promotion. So that's the one new format of publishing. And second one is data curation. And the data you generated from your funded projects are no longer just your personal property. It can, because the government give you money and they have the right demand the data to be stored, made available to the public, to whoever is interested in using the data or in seeing the data. So that's why there's a need to preserve the data, archive the data, and make the data searchable, discoverable, and reusable. So that's another area. And archiving, long-term preservation, storage, retrieval, use of scientific data and methods. So all these three areas are becoming new research areas for information science. So there are many initiatives in research libraries, and I know not many of us in this room are practicing librarians, but what they are doing do have a lot implications for our education, for our curriculum development, for our research projects. So a few years ago, ARL did a research. I think this research I mentioned yesterday as well. The data support and the services in institutions, 45% of them are doing it. Libraries involved in supporting eScience, 73%. And they discovered the pressure points among these respondents include lack of resources. That means not much funding, not much capable personnel. That's the major problem, and difficulty in acquiring the appropriate staff and expertise to provide eScience and the data management or curation services. So there's a lack of workforce in the library who wants to start services to support eScience, to support data-driven research. There's such a big demand. So that's one. And also lack of a unifying direction on campus. This is I think it's easily understandable because IT department and library department, they have their own interpretation about this data-intensive research, data-intensive, X, whatever it is. So I think that these are very important inspirations for information science to develop our new research areas and new research projects. So the data-intensive research raised expectations to library and the information professionals. And, on the one side, we need to have our graduate students, students graduated from our programs, they need to have working knowledge and skills in data science, and this is expected. And there's a focus, in the practice, there's a focus on process, which means data and team science, rather than product. In the past, I think librarians are just sitting there waiting for people, students and the faculty to come to ask questions, and we call this is like the product-oriented service. But now it's there's an emphasis on the process, like librarians, data librarians, no longer sitting in the library, wait for patrons to come to ask them reference questions, but they go out to attend their project meetings, to interview scientists, to understand what their needs are, what problems they have with data management, what they want the library to provide support for their data management. So this is emphasized on process rather than publications. So that said, I have recently done a few projects. The first one, one line of research is on metadata, because I teach metadata, I do research on metadata. So the metadata paper in the last couple of years I've written, one is about metadata infrastructure requirements, and this is a paper accessible from Dublin Core archive. And in this paper, I proposed this metadata infrastructure architectural view and group the metadata elements into different modules, different areas. And this is the first step. And the second step, last year I did a research to study the portability of metadata standards. So we collected a total of about over 4,000 metadata elements from 16 scientific metadata standards, and studied their the portability. And I think we have two measurements for the portability. One is co-occurrence of semantic elements, and the other one is degree of modularity. So these two, and we have some very interesting findings, and it was reported in this paper from last year's. And by the way, the link will take you to the if you go to my website, the paper is linked there as well. Another project I did was last year. It's a 1-year project, and this is using a model called capability maturity model. This model, CNM, short for CNM, this model was developed during the 1980s by Carnegie Mellon University's Software Institute. And this model was used for them to monitor the software development quality. And we borrow this model to to look at research data management. And the link you see here is our website, which is a document that's on the wiki, publicly available. And this model basically help identify organizational strengths and weaknesses, and make process changes to replace weaknesses with strengths. So this is our goal of this project. It was supported by ICPSR and the Sloan Foundation. And the model, basically, we say in data management, we have 5 different levels of maturity. At the first level, data are managed intuitively at a project level without clear goals. Okay, and the second level, data management process is characterized for projects and often reactive. The so-called reactive is, oh, okay, now we can't find the files, so we need to create some naming convention and some file system to make our data more easily discoverable. So that's kind of a reactive data management maturity. And the third level, data management, is characterized for the organization and the community and the proactive. So it's the scale becomes larger, and it's usually at organization, like say an institution or some kind of a research association, a larger research community, like ecological research community, geoscience research community. Usually is at that kind of level. Level 4 will be measured and controlled. So say you have reached level 3, and then the next level of maturity will be you will collect data and define the metrics in order to assess how you did in the process. And level 5 is based on level 4, and then you improve, identify areas that you need to improve. So that's the capability maturity model. And we had a workshop teaching the practitioners how to use this model in their data management projects. So it was I think this was last April, earlier this year. And that's the second project. And the third project that's ongoing, this project is ongoing, is discovering collaboration network structures and the dynamics in big data. The database we use is from Jian. We basically collected the metadata describing the DNA sequences, all those metadata records, and extract them and store them in the MySQL database. And then we also have set up the R server to call data from MySQL database to perform analysis and visualization. So a PhD student and the 2 master students are in the team to perform these analytical and visualization tasks. So the data source is from Jian, and we have a lot of challenges in using this big data. So the major problem is named entity resolution. So we need to have this resolution because in Jian, the author names only have last name and the initial first name initial, middle name initial, and the initial, middle name initial, excuse me, is not consistently used. So there's that involves, we don't want to over estimate or over calculate, overcount or undercount the scientific collaboration scale or network size, and the attributes and all that. So we need to do disambiguation, and we use some natural language processing algorithms and machine learning methods to disambiguate the named entities. And the data quality, we used many different ways to ensure that our data is correctly parsed and accurately mapped, and all these. There's many details need to. Sometimes we think we already done the work, and some error pop up, some inconsistencies, strange stuff pops up, then we have to go back to recheck again. So there's a lot of these iterative processing, and there's a lot of all these errors and inconsistencies have a lot to do with submission and submission behaviors among the biological scientists. So, and internal relationship, this is just showing the I think it's too hard to explain because it takes a lot of time to show that. But I think I can show you one example is this diagram. So basically the annotations, there are 149, close to 150 million annotations. And for references, which are papers, there are 1 million and 1.3 or close to 1.4 million papers. Patents, 26 millions. Publications, here's different. Anyway, direct submissions are the submission of the actual DNA sequence data. Authors, we got, I think it's 500,000. Consortia, some data are not submitted by individual scientists, but by a consortium. So that's another case. Countries, 125 countries. So far we counted. Okay, so finally, I think I'm doing good. Finally, data-driven science generates vast amount of data and it provides opportunities for librarians and information professionals, for a lot of job opportunities and opportunities to develop new services. And for researchers like us, many of us, we can also think about, we have new data sources available for us to conduct new research. All these data repositories. Of course, we cannot do scientific research using those scientific data sets, but the metadata describing those data sets is a great data source for us to conduct all kinds of research. And so I think that means we will also have the opportunity to use these data source to develop new theories, new models, and new frameworks, and and which can go back to our teaching. We can educate our students better. Okay, thank you. Obrigado. Wants to come up? Any questions? Or are you too tired to think strictly?
I have one.
Okay.
Yeah, do you think in Portuguese is better?
You can speak Portuguese for your question. I will do it. Yeah.
Você falou na sua palestra sobre interoperabilidade.
Oh, speak the microphone.
Você falou na sua palestra a respeito de interoperabilidade. Eu queria saber como que isso está sendo pesquisado lá no contexto dos metadados, na pesquisa que vocês estão executando em Syracuse.
You mean the metadata research?
Yes.
Okay. Well, unfortunately, in Syracuse, doing metadata research, I'm the only one. So all I reported here are the research that I've done so far. So the portability research, the portability of metadata standard, that's the project from last year. But I haven't, because I was engaged in other projects, I haven't had time to do it further. Interoperability?
Yes.
I didn't do research on interoperability, but my co-author did. Yeah. My metadata research is primarily at the theoretical level, not on the practical level. So when you talk about, so people, I think to say this way, the metadata research that I did was mainly focused on metadata standards and the application, the strengths and the disadvantages, pros and cons using those large metadata standards. So I'm looking at metadata from a high level rather than from, say, on the, I create metadata records for a museum object. I didn't do that kind of job, but I'm doing high level job. Yeah. Yeah. Come. I want to make sure I can carry this so I won't break it again. Obrigada.
Sim, a senhora falou sobre a questão dos. Deixa eu só voltar. Sobre os serviços que as bibliotecas universitárias de pesquisa podem oferecer para os pesquisadores. E digamos, além de ser mestranda, eu também trabalho com relação, digamos, com a biblioteca universitária. E eu fiquei assim pensando, digamos, que serviços que digamos, meu mestrado é pesquisa digamos, eu estou pensando sobre repositórios de dados de pesquisa. E eu fico pensando assim, digamos, que serviços as bibliotecas podem oferecer para os seus pesquisadores e ali, assim, digamos, o que motivou, digamos que aqui no Brasil a gente tem pouca ainda literatura, né, o professor sabe, assim, que temos pouca literatura sobre isso em português. Eu tenho, tanto que a maioria da minha literatura tem sido em inglês, em outras línguas, e digamos, aqui no Brasil ainda não tem a política, aqui no exterior, pelo menos eu tenho visto que as agências de fomento estão pedindo que que quem solicite o financiamento tenha o seu plano, o seu projeto de gerenciamento de dados, de pesquisa, e que deposite seus dados. A senhora acha que isso foi um dos impulsos para que os pesquisadores começassem a procurar esses serviços e que as bibliotecas também passassem a oferecer? Ou digamos, o dilúvio de dados foi também motivador? O que pesou mais? O financiamento ou o dilúvio de dados para as bibliotecas universitárias começarem a oferecer esses serviços?
Obrigada. Good question. I think I got the same questions when I give, similar lectures to the Chinese librarian community, because they are at the same situation. They are in the same situation as Brazil is in, I believe. I think that in US or in Europe, the reason that the research libraries can can do this or is motivated to are motivated to do this is because there is a policy from higher up. So policies from higher up is very important, but how the higher up can think, can think of such a policy to, to distribute, to enforce, to mandate all the researchers to do this. I think it does need librarians like you or other people, other not present in this room, to push, because I think I can just give one example. ARL, Association for Research Libraries, they have office in the capital city in Washington D.C., and they have close relationship with those funding agencies. And when librarians voice something at a conference or through some, and they can go to those funding agencies and make suggestions, or even even push, because there are other offices like a council for library library resources. It's an organization, kind of policy office in DC, and they can also bring their comments and their whatever, to push the higher up. And I think that the data management is not something that the NSF and NIH just, oh, we need to do this. It's not like that. It's because someone in the practice have met this problem, and they discussed, and they probably made this kind of a recommendation, suggestion over and over, and finally the higher up heard of us, and then they issue this policy, becomes mandate, and then when it's mandate, everyone has to follow. So with this mandate policy, if you are not if you do not have data management plan, the funding, even no matter how good your proposals are, you cannot be funded. That's very important. Yeah.
Boa noite, professora. Obrigada pela palestra e pelo curso, que foi muito bom para nós. Eu tenho duas questões, vou tentar reduzir ao máximo assim, a pergunta. A primeira é sobre curadoria, que aqui no Brasil ainda não vi nenhum trabalho ou prática do profissional da informação ou bibliotecário trabalhando na atividade de curadoria dos dados, curadoria da informação. Eu acho assim, principalmente relacionada à aquisição de conhecimento para uma base de dados. Então, eu gostaria de saber como tem sido esse trabalho, né, se vocês têm alguma coisa relacionada a esse assunto. E a outra questão é relacionada à medicina baseada em evidência, que hoje tem se usado muito, e percebe-se também que cada vez mais o bibliotecário, o profissional da informação tem sido convidado para trabalhar nessa área. Então, eu gostaria também de saber como que isso está inserido nesse contexto e se há discussão a respeito dessas duas questões.
Okay, I'll try to answer the first question. I think I know better about the first question, but for the second question, I'll try my best. The first question, kind of forgot. Oh, curation. Okay, sorry. For the curation, if you are looking for resources, there is a conference called International Digital Data Curation Conference that's organized by UK, DCC Center. That's one, and they have paper for open access. So that's one source to search, look for. But if you look for educational programs, UIUC has a certificate program called Data Curation, and UNC Chapel Hill has a professor called Helen Thibault. She has done many workshops on digital digital curation. So that's so if you're looking for sources, those are the places to look for. But I think for digital curation, it's it's intertangled with data repositories, institutional repositories, and it really, in order to effectively apply this concept and develop a project, and this project will, will ensure its, you will ensure its success. You would have to do a careful analysis and the planning, because for each data curation, for each digital curation project, you could curate data sets, you could curate publications, right? And then also there's the disciplines. Are you going to do it for the whole university, or are you going to do just for, say, geology or biology? So there are many of these questions need to be think through first, and you identify. So say you identified all these, but there's one thing you are not sure. I don't know. Maybe I can get funding for the first 2 years, but I have no idea how I'm going to survive after the funding ends. So you would need to think through all these questions, and this is also what we need to teach our students, to think in the in a productive way, rather than to just jumping in, design something, and then that's not going to last. So that's not what we want. So I think it really depends on individual situations. Okay, so after this analysis, and you can probably come up with a good plan. The second question. Oh, evidence-based medicine. Okay. For healthcare, although I did give a workshop to health sciences librarians, they also asked questions similar to yours. I really don't have a good answer for this question, but I think in terms of research data curation or research like evidence-based medicine, there's I think the process and the idea is similar, because when you do evidence-based medicine, you do, I don't know, I understand what Cochrane analysis is in medical research. It's like meta-analysis, but I'm not quite sure exactly evidence-based medicine is. But I think it may be similar to Cochrane analysis, meta-analysis type of thing. So in that case, they have definitely a demand for organize the literature and the data from the literature, and how to organize them, sort them, and compile them, and manage them, so they can conveniently conduct evidence-based analysis, medicine research. That's the best I can think of, but I don't know if I answered your question. Yeah.
Boa noite, professora. Muito bacana a sua apresentação. Eu falei com o Maurício que eu não queria que você fosse embora, que você ficasse aqui para a gente aprender mais. Mas o que eu gostaria de perguntar é o seguinte: aqui no seu último slide, você fala, então, de algumas, da importância dessa quantidade de dados que serão gerados, e eu queria perguntar justamente sobre isso. Ou seja, dali, por exemplo, você fala que depois a gente tem uma quantidade muito grande de dados para gerenciar, e que, por exemplo, seria possível gerar estudos bibliométricos, serviços, novos modelos. Então, minha pergunta é a seguinte: existe já algum estudo implementação dessa gestão de dados que aponte que, de fato, houve novos conhecimentos foram gerados, novos produtos foram gerados, novos projetos foram gerados, novos estudos foram gerados a partir da implementação dessa quantidade grande de dados que precisam ser gerenciados.
I think I did. Yeah. Okay. So for the new data source, so this, I think, in order to answer your question, I have to separate two different aspects of your question. I think for the large data repositories, it generates two kinds of opportunities. One is for practitioners, because it creates jobs. It requires people to, trained professionals to manage this kind of data repository, provide services. For example, the social sciences qualitative database data repository at Harvard, they have full-time staff just for managing this, because when someone submitted a data set, they have staff to review and approve the data set, modify the metadata to ensure the quality, and before publish the data set in their repository. So this is a kind of new job that no one has done before. So this is the new opportunity for practitioners. For researchers, the big data repository, although I don't know how to analyze DNA sequence. I'm not a biologist, right? So, but I am trained as a librarian. I understand the metadata. So the metadata itself has a lot of potential for us to conduct research. For example, the DNA sequence, the gene bank metadata has data about, the date of submission and authors, affiliations, and the taxonomies terms and taxonomy lineage and type of submission and all that, publications, and all these can be used as data source to study, say, the metadata quality control, or design better metadata tools for them to, to manage the metadata, and also, or curate the data, and identify. I already identified some data curation problems from the metadata. So that's another data source, another type of research. I can also use the, affiliation number, affiliation field. I can do recoding to conduct a scientometric research based on the metadata. So that's what I mean. You can use the metadata. You can use the metadata because we understand that data very well to conduct new research. But for practitioners, data repository, themselves are, a job market for them. Yeah.
Bom, vamos encerrar então, agradecendo a professora Jian. We'd like to thank you very much for sharing your knowledge with us. Boa noite a todos. Então.